Okay, our topic for today is the energy of rotation. Now, clearly there's kinetic energy here when you have a rotating object, but it's a little bit difficult at first glance to figure out what that is because we know that, say for a little bit here of mass, that the speed at which it's going depends on the angular velocity omega, but also on the distance that it is, but also on the distance that that little mass element lies at, measured from the axis of rotation to the pivot point. And because that distance is different for each mass, that means all of the little bits of matter are actually going at different speeds, right? You'll have a much greater speed out here when you're further from the rotation point. So to find kinetic energy, at first glance, it looks like we've got a problem because we've got to add up a half times each little kinetic energy for each little bit. Well, fortunately, although the distance is different for each element, the angular velocity omega is the same. So when I replace v with r omega, the omega is a constant. Oh, that's just horrible. Let's write that again. Try that one more time here. So bracket, this is r(i) omega squared. So once again, the omega is a constant, so it comes out of the summation, and the half is a constant, so it comes out of the summation as well. And what we end up summing is mi squared. Now, why is that helpful? Well, because a mass times a distance squared is, pausing for effect, the rotational inertia of that little bit. And so what we've really got here then is we've got a half. This will be the total rotational inertia of the rotating object times omega squared. Now, in a lot of ways, that shouldn't be surprising because in physics 11, in high school physics, we know that kinetic energy is 1/2 mv squared. And we've seen that we can usually just transliterate the physics 11 relationships to get the rotational relationships because the definitions are fundamentally the same. So this is how we find rotational kinetic energy, 1/2 I omega squared. Now, that would be the total kinetic energy for a pure rotation, but sometimes objects have both. So say a rolling object is a good example of that because a rolling object, well, it's rotating, so it's got what we call spin kinetic energy, but it's also moving in a straight line, so it's got good old-fashioned, we'll call it translational or linear kinetic energy. And the total kinetic energy will be the sum of those two, the kinetic energy of translation plus the kinetic energy of rotation. So you'll have to sum the 1/2 mv squared and the 1/2 I omega squared. So this new definition of rotational kinetic energy is just going to enable us to go back through all of the sort of energy conservation problems we've done earlier and then just add in, I guess, interesting situations where the object happens to be rotating as well. So here's a simple example. Let's find the rotational energy of a baseball swing. So in a baseball swing, we'll ignore the translation of the wrists and say, okay, basically this point's at rest. So it's just a pure rotation. And we're told that it's swinging at a constant 15 rads per second, so we know omega. And if we look at this, well, first of all, we know the kinetic energy of rotation is 1/2 inertia times angular velocity squared. We've got the angular velocity. We need to know the inertia, and that depends on the shape. We're going to treat the baseball bat as a rod pivoted about the end, for which the inertia is 1/3 ml squared, where m is the total mass of the object, and that's given as 0.9 kilos or 900 grams, and L is the total length of the bat, which is given as a meter. So this has now been reduced to a calculation. Put mass and length here, get inertia, substitute in inertia, substitute in the omega here. Or I suppose if you wanted, we could do this and just show the substitution down here. So 1/2 of a third is a 1/6. Then we've got 0.9 kilograms. I guess this is worth doing because we'll just see the units emerge here. Now, dimensionally, we're going to have kilograms times meters squared. Meters times radian is just meter, so radian is a dimensionless measure of length. And so we end up with units is going to be kilogram meters squared per second squared. And that's great because that's a joule. And all energy units should be in joules. So let's next find the total kinetic energy of a rolling tire. So this previous example, we just found the rotational energy. Now when we say the total kinetic energy, we mean both. That's going to be, so kinetic energy total is going to be the translational energy plus the rotational energy. Now, there's a little bit of algebra that's often helpful in this situation because we know that rotational energy is half I omega squared, but then we know that inertia depends on the shape. So because this is a hoop, we know hoop inertia is mass times the radius of the hoop squared. If it's rolling with no slip, then we know that V is R omega, or that omega is V over R. And of course, we still have to square that. So this is an expression then for the rotational energy. We still have the translational energy. Now I'm just making sure that I use the same m because it's the mass of the object. So when you simplify this, you get 1/2 mv squared plus 1/2 mv squared. And using the lost art of fractions, a half of something plus a half of something is the whole. And so we see that the total kinetic energy is just mv squared, and that there's an equal part translation and rotation in this case. So we could substitute in the 8 kilograms and the 60 kph, although we'll need to convert that, of course, because there's 1,000 meters in a kilometer, and then an hour is 3,600 seconds. So this is probably, well, let's just pause and work that out. So it's 16.6 meters per second. 16.6 repeating. So now we can substitute in the 8, that's a mess, the 8 kilograms of tire mass and the 16.6 repeating meters per second squared of speed, and then we can work out what the kinetic energy is. Again, it'll be in joules. And that's the total kinetic energy of that rolling object. So now an algebra challenge for you. Let's find the expression for the total kinetic energy of a rolling ball or a rolling sphere. Try repeating the previous process and simplifying the fractions. Pause the video, and then come back and we'll have a look at my solution. Try this on your own. Okay, so hopefully you were able to get this far. So we sum the two kinetic energies, half I omega squared. For a sphere, the inertia is 2/5 mr squared. For rolling, without slipping, omega will be V over R. So the rotational kinetic energy simplifies to 1/5. Now, when you add the translational kinetic energy, you get a half plus 1/5 mv squared. Using the lost art of fractions, finding a common denominator will be 10. We end up with 7/10 mv squared. That's an expression for the total kinetic energy of a rolling ball. And you may recall in the lab, we ended up using an expression like this when we looked at the conservation of energy lab. We had to include both the rotational and translational energy of a ball bearing rolling through a tube. Okay, so now it's time to get back to conservation of mechanical energy problems. So if we let a ball roll down a ramp and ask to find its final speed, well, sorry, that's mislabeled. There's the speed v. This will be the angular speed omega. So it is rolling down here at the bottom. Something that's important to note is if you're rolling without slipping, then there's a force of static friction that's making you roll. We remarked earlier in the course that there must be friction, and the reason there must be friction is that you need a torque to make it roll. And so friction acting a distance r away from the center gives you torque. But that friction is actually static friction because this point is at rest when it's at rolling. Now the good news about that is that that means that there's no thermal energy. There's no heat created because that point's at rest. And as a result, what happens is that mechanical energy is conserved. So when we write out the work energy theorem in the modified form, energy at the beginning plus work by non-conservative forces equals energy at the end, this term is actually 0 because it's rolling. Now, the static friction is still doing work, but the work that it's doing is converting potential energy into rotational energy. So in, my goodness, so many emails. In physics 11, it would just be the potential energy of the object getting transformed into good old half mv squared. But here, because it's rolling due to the static friction, there's actually both kinetic energies here. Now, this is a ball, and these two kinetic energies, we just came up with an expression for that. From the previous example, we know that's 7/10 mv squared. Potential energy we know is mgh. So just repeating that derivation really isn't a good use of time, so we'll just use the result. And now we want to find an expression for the speed. So the mass cancels. We cross multiply the 10 over 7 using the lost art of cross multiplication. That's v squared. We then take the square root to find the speed. Okay, so that's a typical conservation of energy problem when we have problem involving rotation. Here's another interesting conservation of energy problem. So we've got a tree and it falls to the ground. So it starts up like that, and then later it has just about to hit the ground here and is now speed omega. So here it starts at rest. Now this is a pure rotation. So at the end, there's just kinetic energy of rotation. We can treat this then as a pure rotation, so we don't need to worry about translational energy. Now we'll ignore any work that's done by the roots lifting soil up here, so we'll say there's no gains or losses of mechanical energy. And at the beginning, there's just potential energy for the tree. Now, what's a bit complicated here is that the potential energy varies, obviously, because down here there's not very much height. Up here, there's lots of height. Well, the way that we deal with this is we say the potential energy at the beginning is we can look at the potential energy of the center of mass, because however much mass there is down below height L over 2, there's as much above, that same distance above L over 2. So on average, all of the tree is at L over 2, or you can just find the potential energy of the center of mass. Whichever way you prefer, the potential energy of the tree initially is mg L over 2. Then at the end, we have a pure rotation. We've got 1/2 I omega squared. Now I, it's a rod pivoted about its end, so that's 1/3 m all squared. For omega, we're just going to leave it as omega now. We could, of course, find an expression for v, the tip, the speed of the tip. V is just going to be L omega if we ever need that. But let's just leave it as omega because we're asked to find the rotational speed when it impacts the ground. Now, mass cancels. We're going to, oh, I forgot the half here. Sorry about that. It's 1/2. Then this part here is the inertia times omega squared. So the half also disappears. And then, so we're going to cross multiply. It's going to be 3gl over L squared. So that's 3g over L is omega squared. So omega is the root of 3g over L. And that is the final speed of rotation omega. The speed of the tip, then, is that value of omega times the length. Now it responds. Fabulous. We got some major sluggishness going on here. Okay. So the tip will be omega L. So that's root 3g over L times L. Well, L over square root of L, you can show, just reduces to this expression here. All right, so the next thing we'll talk about briefly is work. Now we know that a work is a force times a distance. The distance for a rotating object, well, that's going to be an arc length, and that is, of course, r times theta. But force times distance, well, that's the torque. And then I guess instead of calling this theta, we should really call it delta theta, the angular displacement. So we see that a work is a torque times an angular displacement. This is assuming a constant torque. Now, that is really just the same. It's the equivalent of physics 11, force times distance. For power, of course, it ends up being work over time. We know in physics 11 that it was a force times a speed, so no surprise for constant speeds that the power ends up being the product of torque and angular velocity. So a really simple question here. Let's imagine that we have a disk, and then we exert a force along the edge of 75 newtons. So this might be looking at it in top view, right? We're looking down from above. We push it for 3 seconds. Oh, there's some frictional torque. So there's some resistance in the bearings there. And we want to find the work that we do and the work done by friction. So for rotation, a work is a torque times an angular displacement. And so the torque is going to be the product of the force and the distance from the pivot point. Well, that's just the radius of the disk. So we need to find out, we know the force, we know the radius. We don't know the angular displacement yet. We're going to have to think about that a little bit. The next thing we want to do is we want to find the work done by friction. I'm not finished this yet, but I'm going to pursue it a little bit later. So the work done by friction is again going to be a torque times a displacement. Well, the torque of friction is given. It's 120 Newton meters. Because that's dissipation, opposite to motion, the work done will be negative. So again, we need to know the angular displacement. I guess I should go back here and I should put the 75 newtons times the 5 meters in here. And then we still need the angular displacement. So how do we find the angular displacement? Because clearly both of these results rely on it. Well, we're going to use sum of the torques is I alpha. So we've got an applied force torque of 75 times 5, a friction torque of 120. That's going to equal I times alpha, and the inertia is 1/2 mr squared. So the mass of this disk is given, I hope, is 100 kilograms. There we go. And the radius is 5 meters. So you can find alpha, and then we're told that it starts at rest and it accelerates for, I believe it is 3 seconds. So because it starts at rest, this term is just 0. So we're just going to do 1/2 alpha times 3 seconds squared, and then that will give us our angular displacement. Now, once we've got our angular displacement, we can go back and we can find the two work terms right here. This one and this one. So let's do that calculation. Okay, so solving the net torque equation for the angular acceleration, I get 0.204 rads per second squared. And then doing kinematics, I find 0.918 rads of angular displacement, so almost a radian. Putting that back in, I get 344 joules of work done by the tangential force, pushing along the edge. And then I get minus 110 joules of frictional losses. So now for the total or net work done, I just add those two up. So that was 344 minus 110, so that's about 234 joules of net work done. Now, for the final speed, well, a couple of ways to do it. I could just do kinematics, because I know the angular acceleration in time. Now, we have to be a little bit careful. This W is work, and this isn't a W at all. This is an omega. So it starts at rest. It accelerates at 0.204 rads per second squared for 3 seconds. So that should give me a final speed of 0.612 rads per second. Alternatively, the total work done should be the kinetic energy change. And kinetic energy we recall as 1/2 I omega squared. So it's 1/2 I omega final squared minus 1/2 I omega initial squared. Sorry to squeeze you in there. Omega initial is just 0. So we could take this total work of 234 joules, cross multiply the 2, divide by the inertia, take the square root to get the final omega. Should be the same answer. So we've just seen that we can find work using a torque times an angular displacement. That's just like physics 11, work is FD. But of course, we can find work using the work energy theorem. Energy at the beginning plus work by non-conservative forces equals energy at the end. And that was the same as the physics 11 relationship. So here's a typical problem. We'll find the work done to stop the rotation of the Earth. So first we visualize. So it starts off with the Earth rotating with its usual initial angular speed. And then at the end, well, it's at rest. So we don't know the force that's being applied. We don't know the torque. And we don't know how far it rotates. So although this is true, it's not useful in terms of finding the work. So we'll use the other possible technique, which is the change in energy. At the beginning, we've got rotational kinetic energy for the Earth. We do some work and we end up with nothing. So how do we find rotational kinetic energy? Well, it's half I omega initial squared. Now this W, I'm going to write it out as work so that we don't confuse it with angular velocity, omega. Now a couple of things here. Okay, for the Earth, it's a ball, so that'll be a sphere, 2/5 mr squared. And for the initial angular velocity of the Earth, I indicated several times, a little trick for finding that, you use, when it's spinning at a constant speed, speed is a distance over a time. This is 2 pi radians of rotation over 1 day, or 86,400 seconds. So putting that all together, we get a half times 2/5 mr squared, and then the omega is 2 pi rads over 86,400 seconds, and then we have to square that. And then we can solve this equation for the work done in stopping the Earth. And at this point, we'll conclude our videos, because we have thus far, our results in question show us that kinetic energy is 1/2 I omega squared. That's the rotational kinetic energy. And then we've got good old-fashioned kinetic energy as well, half mv squared, good old-fashioned potential energy, mgh. So this just enters into the standard energy analysis involving the work energy theorem. We've also seen that we can find work both from the work energy theorem, but also from finding a torque times an angular displacement. And so we'll pick up at this point in class, and we'll do some more practice problems involving the work energy theorem and involving rotation.